Okay, so let's start. My name is Amir, and I am an assistant professor at the departments of computer science and mathematics here at HKUST. And I generally teach algorithms and also blockchain. And in this session here, I'm going to talk a little bit about the basics of how blockchains and especially Bitcoin work. And hopefully this will convince you to also take the blockchain course. So let me start. You've all probably heard about blockchains before. The goal of my talk today is to just give you some technical expertise here without getting into any of the mathematics. And just making sure that you understand whenever someone's talking about blockchains, what's going on. Okay. So let me start with this very famous sentence that you have probably seen all over, especially probably on Wikipedia, in different talks and so on. When people explain what Bitcoin is, they usually say something like this. They say that Bitcoin is basically a collection of buzzwords. It's a decentralized, trustless, pseudonymous cryptocurrency that can be transferred on the peer-to-peer Bitcoin network. And of course, you've heard these words as well. It uses blockchain, it uses proof of work. So I want to tell you what all of these things mean. And if you've already taken my blockchain course, you already know all of these things, so I'm sorry that you were forced to be here. Okay, so what do these words mean? Let's start with cryptocurrency. So what is a cryptocurrency? A cryptocurrency is basically a currency that uses cryptography. That's where the word crypto comes. And actually, for my generation, when we used to say crypto, it meant cryptography, not a cryptocurrency. So what is a digital currency that uses cryptography? It's basically a digital currency that uses digital signatures. But now I have to define two more words for you. I have to say what cryptography is and what digital signatures are. So cryptography is basically the field of computer science that tries to study ciphers and problems like encryption and decryption and secure communication and things like that. So every time you open your email account, if you still do that, that's done using cryptography. And probably all of the messengers that you have on your phone right now also use some sort of cryptography. So the basic idea is, let's say I open my Gmail account and I want to read my emails. And let's say that my emails are encoded as some message M. So if Gmail just sends me this message M on the internet, then anyone else who can see our communication can also know about the contents of that message, right? So for example, my internet service provider would be able to read my emails, or probably my government would be able to do that. And of course, we don't want that to happen. So usually what Gmail does and what any other mail server does is that they first encrypt the message and then send me an encrypted message. And then the idea is that I should be the only one who can decrypt this message and actually read my own emails. So this is a very simple idea. Let's make it a little bit more exact, what I'm talking about here. So as any person on the internet or in any kind of digital communication, I would usually have two different keys, and this is what we call a key pair. So I will usually have a public key and a secret key. And the idea is that I'm the only person in the world who knows my secret key, but everyone else in the world can know my public key. That's in the name, it's public. So if someone wants to send me a message, they have to encrypt it. And in order to do the encryption, they will need my public key. But then in order to read that message, in order to decrypt it, the secret key is needed. And I'm the only one who has this secret key. So I'm the only one who can decrypt messages that were encrypted using my public key, and no one else can read messages that belong to me. So this is the basic idea of encryption. I'm not going to get into mathematical details of how we actually create these encryption and decryption functions. All I need you to know is that such a system is possible. I can have two functions for encryption and decryption such that anyone can encrypt using the public key that everyone knows, and only I can decrypt using the secret key that I'm the only one who knows. Okay. So this is the basics of cryptography. But now, what about digital signatures? So when I said that Bitcoin is a cryptocurrency that uses and heavily relies on digital signatures, what does that mean exactly? Well, it's again a similar situation. We have two different keys. There is a public key that everyone knows about. There is a secret key that only I know. And in order to sign some message or sign some document, I need to have the secret key. But after I sign it using my secret key, anyone else would be able to verify that signature using the public key. So it's kind of like a digital version of real-world signatures. Anyone else who knows my signature can verify that it's really my signature, but I'm the only one who can actually create that signature. Okay? So that's all I want you to know about digital signatures. This is all the background that you need in order to understand how Bitcoin works, which is the main topic here. And of course, I want no one else to be able to forge my signature, and I have that property as well. Okay. So now that we've defined cryptocurrency, I can already tell you how I use digital signatures. So if I want to send some money to you, I have to show the world that I actually own that money, right? And as the owner of that money, I have to show the world that I'm really consenting to that money being transferred to someone else. So I would do that using a signature. So if Alice wants to send money to Bob, the transaction that sends the money from Alice to Bob has to have Alice's signature. That's the use case of signatures there. But I'm just going to continue with defining these different terms here. And then after I define all of them, I'll get back and tell you how the system actually works. Okay, so we have a cryptocurrency, but it's supposed to be on a peer-to-peer network. So what does that mean? Well, a network is basically just a bunch of computers that can communicate with each other. That's super simple. So you can just imagine a bunch of computers on the internet or connected to each other in any other way. But what does the peer-to-peer part mean? Well, it means that all of the nodes in our network, all of the computers in our network are in a sense equal. They don't have different roles. They don't have different permissions. There is nothing that one computer can do that others cannot. Okay? So in contrast to this, if you look at like traditional banking, that's more of a server-client situation. So if you want to work with your traditional bank, you open their app and you would probably send some messages to the server of your bank. And it's actually the server who has control over all the money and the account balances and so on. And if you have a bank which has all the information, each one of the clients would only communicate with the bank, right? So if two different people have bank accounts with the same bank here in Hong Kong, you never have to communicate with another client of the bank. You're always communicating with your bank. So in that sense, the bank is special and the bank is like a server and you're the clients. But in the Bitcoin system, no one's special. Everyone is equal to everyone else. So you will just have a bunch of computers and some of them are connected to some of the other ones, and none of them have any special permissions. Okay. So now we know some of the words. We know cryptocurrency, we know peer-to-peer, we know what network is. Let's go on and let's define the other words. Okay, decentralized. This is the most widely misunderstood keyword here. So when people think about a decentralized currency such as Bitcoin, they tend to dream whatever they like. And it's like they feel like they have perfect privacy, that no one can check what they're doing and things like that. But actually, the definition of decentralization is quite different. It's just that everyone on the network is equal. So there is no central bank, there is no central government. No one can decide who owns some coin or some money. No one can confiscate anyone's money. Yeah, there's basically no judge, no system like that. It's just that everyone is equal. So if everyone is equal, how would you know when a transaction happens? So let's say I want to send some money to someone else. How would the rest of the world know that I have that money? And how would they know that this transaction has happened? And actually, the solution for that is pretty easy. We just have a gossip protocol. So whenever a transaction happens, I create the transaction, and of course, I have to sign it. And then I just tell the transaction to someone else in the network. And then they just keep gossiping about it. So anyone who hears about the transaction, any computer on the network who hears about the transaction, would tell all of their neighbors, all of the other computers that they're connected to about that particular transaction. So we don't have a server. And in a way, this is good, because in an architecture like this, where you have a centralized server, if that server goes down, or if for some reason it's disabled, for example, suppose that the government doesn't like Bitcoin and wants to turn it off, they can just attack the server and stop it from giving you service. But in a case like this, it doesn't really matter. If any of the computers go offline or get disconnected or something happens to them, the network would still keep running. Okay, so that's the decentralization part. Let's go on. So the next one is actually another misconception that exists about Bitcoin. So people tend to think that Bitcoin transactions are anonymous. And that's actually not true. So Bitcoin doesn't have perfect anonymity. And the reason for that is that even though you don't really use your real world identity, there is some identity on Bitcoin. And the identity is basically the key pair that I talked about that you would use for creating signatures. So you have some keys that you use for creating signatures. There was a public key, there was a secret key. The public key is going to be your identity on the network. So your identity on the network is basically a key, which is like a sequence of, I don't know, 140 digits. And it's not really connected to your real world identity. So in that sense, yes, Bitcoin is anonymous. But on the other hand, whenever you're creating a transaction, whenever you are trying to send money to someone else, you have to use your network identity. You have to use your public key and secret key. And in that sense, it's not really anonymous. So that's why we call it pseudonymous, like pseudo-anonymous. Okay, but a really important point here is that there is no real world identity verification. And so as a person who joins this network, you can create as many network identities as you like. Or another way of thinking about this is that you can create as many Bitcoin accounts as you like. And you don't have to even announce this to anyone. You can just create it on your own machine. So as long as you create a key pair, that's an account on Bitcoin. Okay. Last sentence says that Bitcoin uses a blockchain and a proof of work protocol for consensus. So I have to now define what consensus means. So consensus means agreement, and it means agreement among everyone. So we want everyone on the network to reach an agreement about the ownership of the coins. We want everyone on the network to agree that, for example, Alice owns 5 coins. Okay? Of course, there is some small asterisk there, and it's like everyone who correctly follows the rules. Like if you're not following the rules, then you will not get the consensus. Okay, so we want there to be no disagreement about ownership. And this is actually something that would be really challenging. Because again, if you think about the traditional systems, if you think about a bank or a banking system with a central bank, then there is, of course, really no disagreement about the ownership, because you own your money if and only if your bank says that you own it. So your balance is shown to you. It's saved somewhere in the database of your bank or maybe the central bank of your country. And that's it. There is no challenging that, and there is no way that two different people can have a disagreement about someone's balance. But as soon as we go to a decentralized system, as soon as we have so many different nodes on the network and all of them are equal, it suddenly becomes much harder to get consensus. But anyway, I'm just defining my terms. So consensus means everyone agrees about who owns how much. Okay. The other word, which is one of the biggest buzzwords, is blockchain. So what is a blockchain? A blockchain is just a history of all the transactions that have happened from the beginning of the system, which in case of Bitcoin was like 2008 until now. So if you just have a list of all the transactions that have happened, that's basically what you have on the blockchain. And a very important property of a blockchain is that you can only add new entries to the end of it because you can only do new transactions. But you shouldn't be able to change entries that were already on the blockchain. So you shouldn't be able to go back and say, I did this transaction in 2009 and now I want to change it. That's not going to be possible. Now, again, we have to go back to the decentralization. So we said that all the nodes on the network are equal. If everyone is equal to everyone else, who keeps track of the blockchain? Who keeps track of the transactions that have happened until now? And the answer to that is everyone. So if you're on this network, you have to keep track of all the transactions that have happened until from 2008 until now. Okay. So, and this is usually how people show a blockchain. Let me go on. So what's proof of work? This is another keyword again. So our problem is we have this blockchain, which has a huge number of transactions. It's basically all the transactions that people have done on Bitcoin since 2008. And we want everyone to agree about this, right? Each person or each computer on the network has their own copy of the blockchain, but we have to somehow make sure that there is an agreement, there is consensus. Now, the way we reach this consensus is, at least in Bitcoin, using something called proof of work. And I will show you more details about proof of work soon. But basically, the idea is that you have to solve a really hard computational puzzle. And that's why you've all probably heard that Bitcoin uses more electricity than some countries, maybe more than Ireland or something like that. So I will get back to this part. Finally, and this is probably the most important word and the one that is often omitted, the system is trustless. And by trustless, I mean that we don't ever trust anyone. So generally, the ethos in the blockchain sphere is that we are very paranoid people. We don't trust anyone or any group of people, and we just assume that everyone is motivated by their own economic gain and payoff, and everyone just wants to make as much money as possible. So we would assume that if we do something wrong so that people can steal our money, they will steal our money. And that's why Bitcoin and other cryptocurrencies are safe, because even with these assumptions, we show that they work. So that's the trustless part. Okay. But now I'm finally ready to get into the details of how things actually work. So what is a transaction on Bitcoin? Well, we know what a transaction is in the real world, right? In the real world scenario, a transaction is just that someone is sending money to someone else. But what kind of information should I include in that transaction? So suppose that someone, for example, Alice, wants to send 1 Bitcoin to Bob. She should, of course, create a transaction, but what information should there be in this transaction? Well, of course, we need Alice's identity. And by identity, I don't mean real world identity. I just mean the keys, or more specifically, the public key. And that's because everyone else on the network should be able to verify that this person who is trying to send this money actually has enough money to send it, right? It should also contain Bob's identity, because we have to know where the money is going to be sent. Of course, we need the amount, but there is two more parts to this. So one of them is something that I've already talked about, and that's the signature of Alice. So if this transaction does not require a digital signature from Alice, then anyone else can create this transaction and can spend Alice's money. So we definitely want the transaction to be signed by the originator, by Alice. But also, Alice has to prove that she really has the amount of coins that she's trying to send. And the way she can do that is that she can just point to a previous transaction and say, here's where I received my 1 Bitcoin. So I received my 1 Bitcoin as at a transaction with the following number or the following hash. And now I'm spending that 1 Bitcoin here. I'm sending that 1 Bitcoin to Bob. So this is basically proof of ownership. So we need the identity of the person sending the transaction, identity of the receiver, the amount, proof of ownership, and proof of consent. And proof of consent is the signature. Okay, but let's say now Alice creates this transaction on her own machine, on her own computer. What should she do with it? Well, the answer is quite simple. Just tell it to someone else in the network. So let's say that Alice tells the transaction to this computer in the network. Now, what does the protocol say you should do when you're a member of this network and you hear a transaction? Well, you have to first verify that the transaction is a valid transaction, in the sense that you have to verify that Alice had the money that she wanted to spend, and you have to verify the signature, making sure that this is not a fake transaction, and so on. But after you verify the signature and the ownership, and it passes all those checks, you would just announce the transaction to everyone else in the network. But you can't directly announce to everyone else because you're not connected to everyone else. So you just announce it to everyone that you know, to everyone that you're connected to. So this computer here would announce the transaction to this one, and this one. But then the protocol continues. So each one of these computers would verify that the transaction is a valid transaction. And if it is valid, they would each announce it to their own neighbors, to the other computers that they know about. And so the idea is that this is a gossip protocol, and eventually everyone would hear the transaction. Everyone would eventually hear the gossip. Okay? So several questions exist here. So the first question is this process private? So can anyone find out about the real world identity of Alice and Bob from this transaction? Well, it is private because we're only using the keys of Alice and Bob, the public keys of Alice and Bob here. And generally, no one has a way of connecting those to real world identities, at least until this point. So we have privacy. Also, Alice cannot spend any money that she doesn't have because that's already checked. We already have a check for that. And no one else can spend Alice's money because we're checking her signature. So all of these things are good. And of course, we just said that after a while, everyone would know that Alice has sent 1 Bitcoin to Bob. So is this enough for us to have consensus? Does this mean that everyone on the network now agrees about everything and we're fine and we can go home? Well, not really. And here's the problem. The problem is what we call double spending. So let's say I'm Alice, and let's say I have 1 Bitcoin. I can create 2 transactions, and in one of my transactions, I can send my coin to Bob. And then I can create another transaction, maybe at the same time, and send that same coin to Carol. So let's say I have 2 transactions here. So transaction 1 is sending the money to Bob. And transaction 2 is sending the exact same coin to Carol. Now, as Alice, I can try something really weird here. I can tell this computer about transaction 1. And then maybe I can go to another part of the network and tell some other computer on the network, some other node about transaction 2. Now what happens? Well, this computer, which knows about transaction 1, verifies that transaction 1 is correct. It's a valid transaction. And the money was not spent. So this computer would just propagate transaction 1. It would send transaction 1 here, and also to this one. At the same time, this other computer has heard about transaction 2, but maybe hasn't heard about transaction 1 yet. So it tells others about transaction 2. Okay. Now, and this continues. Now, at some point, every node in the network would hear about both transactions, right? So for example, this node here heard about transaction 2, but then they will also hear about transaction 1 after a while. And also this node has heard about transaction 1, but after a while, they will hear about transaction 2. But the problem is there is no way for any of the nodes in this network to say which transaction happened first, right? So if Alice created transaction 1 first, then by the time she created transaction 2, she didn't have any money left. So transaction 2 should be invalid. But if Alice created transaction 2 first, then transaction 1 should be invalid. Now, honestly, we don't care that much about Alice. So we would be fine if either one of these transactions gets into the consensus. So Alice has cheated, whatever. I just want to make sure that the network gets a consensus about which transaction is valid and which one is not. But the problem here is that our network is now basically divided in two. There are people on the network who have heard about transaction 1 first. And these are people who think that transaction 1 happened first. So these computers or nodes heard about transaction 1 first. And these ones heard about transaction 2 first. So the ones who've heard about transaction 1 first think that Alice has sent her money to Bob. And so now Bob is the owner of that 1 Bitcoin. And then later on, when Alice tried to send transaction 2, that was invalid because she didn't have money. And so Carol doesn't own anything. But on the other side of the network, people think that transaction 2 came first. So Carol owns the 1 Bitcoin. And then later on, Alice tried transaction 1, and that was invalid. So Bob doesn't own anything. So you see, the problem is not just for the cheater, it's for everyone else. And we need to really find a way to get to consensus. It doesn't matter which one of these 2 transactions gets into the consensus, but we have to make sure that after a short amount of time, everyone on the network agrees again. So this is the problem of double spending. Now, let's continue and let's see how we can solve this problem using what we call a blockchain protocol. Okay. So the idea here is pretty simple. The idea is that as a node on the network, instead of just keeping track of transactions, we ask everyone to keep track of 2 types of transactions. There are transactions that are already finalized, so transactions that you know are in the consensus. And these will go into the second category here, which we call the blockchain. But then I would also keep track of some transactions that I have seen on the network. So someone else in the network has told me about these transactions, but I still don't know if these transactions are part of the consensus. So these are going to be called the mempool transactions. So the transactions that are not finalized are in the mempool. The transactions that are finalized are on the blockchain. Now, adding to the mempool is quite easy. Whenever someone tells me about a new transaction, I just check that the transaction passes the simple checks that we had. It has the right signatures, whatever. And then I just add it to the mempool. But adding a transaction to the blockchain is hard. And that's where we have to go into more detail. So first of all, what's our blockchain? Our blockchain is not really a sequence of transactions. Instead, it's going to be a sequence of blocks. And each block is itself a bunch of transactions. Now, why are we doing this? Because we want to have blocks that have almost the same size. So maybe I want each one of my blocks to be 1 megabyte. Okay, so I have a bunch of blocks, and it starts with, let's say, block number 1. So here I have 4 blocks, and each one of these blocks contains a bunch of transactions. And all the transactions that are in the blockchain are considered to be finalized. But of course, as we said before, each node in the network keeps track of their own copy of the blockchain, and we have to make sure that everyone's copy matches everyone else's. Okay, so how do we do this? Well, this is a process called mining, and maybe another keyword that you've heard about Bitcoin. So mining is the process of adding a new block. Let's say I have 4 blocks here, and I want to add a 5th block. What should I do? What should I do so that the rest of the network agrees to add my block to their copies of the blockchain? Well, of course, I have to first create a block. And let's say that I'm a miner, Mindy. I just create a new block. And to create a new block, I have to choose a bunch of valid transactions that are not finalized yet. So I just go through my own mempool, find a bunch of transactions, create a block. Then, as I said before, it should be hard for people to add new blocks. So I can't just add my new block. I have to first solve a really hard mathematical puzzle. This is the part that is called proof of work. And I'm going to be competing with everyone else who wants to add their blocks. And the first person who successfully solves this mathematical puzzle gets to add their block. So that's the idea. And you can now see that this would actually help us in reaching consensus, but it doesn't still guarantee consensus. So instead of just saying that people can tell me their transactions at any time, we say that they have to give me these blocks. And whenever someone wants to add a new block, they have to prove that they have solved a hard puzzle. And solving a hard puzzle, of course, takes a lot of energy. It takes a lot of computational power. So now it's hard to add new blocks. You have to spend a lot of computational power. And of course, since it's hard to add new blocks and it takes a lot of computational power, people are competing, and then it would be kind of unlikely that different people can solve it at the same time. So I can always say that the first person who can solve this problem gets to add their block of transactions. Okay, but what is the puzzle itself? So if you're not a computer scientist, it's completely fine if you don't understand this part. It's just that we have a hard mathematical puzzle and we want to solve it. But if you are a computer scientist, the puzzle is this. I have to find some number n such that when I take the hash of the previous block and the current block that I want to add, and also this number n, then this hash value becomes really small. Now, what is a hash function? Well, I can just give you a super easy definition of this one as well. So a hash function in cryptography is basically a function that gets any string, any sequence of zeros and ones, let's say, of any length as its input, and then it returns another string, which is the hash of the original one. And the output always has some fixed length. So let's say my output is always 256 bits. And what properties do I want this function to have? Well, I want it to be easy to compute the hash. So if I give you some string, some x, it would be easy to compute h of x. And by that, I mean you can compute it in, let's say, linear time. Okay? The other property is that it should be hard to invert the hash function. So if I give you some value y, it's hard to find some x such that the hash of x becomes the desired value y. And finally, I want it to be collision resistant, which means that it should be hard to find two different strings that have the same hash. Okay. Now, why are we taking such a problem? Well, I basically have to find some value n whenever I want to add my block, so that the hash of the previous block, the current block, and this value that I found becomes small. But the hash function is an unpredictable function. So I have no control over what the values of this hash function become. And so the only solution I have for this is to just try different values for this number n here. So I would just try maybe randomly, or maybe I start from 0, then go to 1, 2, 3, so on. I try all the possibilities maybe for n, or maybe I try randomly. Okay. Most miners actually do it randomly. So the miner Mindy would just try random values of n and keep computing their hash until she gets lucky and she finds a value that is small. And then at that point, she can add the block. But now here's the nice part. The luck of every miner, the probability of every miner being able to add the next block, is proportional to her computational power. It's proportional to how many hashes they can compute every second. If you have more computational power, if you have a supercomputer, you can maybe compute a lot of hashes. Maybe you can compute, I don't know, 10 to the power of 12 hashes per second. But if you are just using a normal laptop, you might be able to only compute 10,000 hashes per second. So as a miner, as someone who wants to add blocks, you have more luck, you have more probability of being the one who adds the next block if you have more computational power. Okay. And this is also the reason why Bitcoin is using so much energy, because everyone is competing to solve this. So we're wasting a lot of computational resources on solving this really useless problem. But the whole idea is that it usually gives us a unique winner. It usually gives us a unique miner who's the one who could solve the problem first and can add the next block. Okay. But let's say you're the miner, let's say you're Mindy, and you've created your new block, and you've also made sure that the hash is small, so you've found the right value, you've solved the computational puzzle. So what do you do with it now? Again, the answer is just tell it to someone else on the network. Or actually, in practice, tell it to as many people as you can. And then again, when you give someone a new block, let's say this time I give my block to this computer, they will again run the gossip protocol. Well, first they check that your block is valid. And checking it is easy because they just have to compute the hash function, and that was an easy process. So they can check that the hash is small. They can check that all the transactions in this block are valid. And if that's the case, then the whole block is valid. And they would just send this block to all of their neighbors. And then this process would continue. And eventually, everyone in the network would hear about this block. OK. So if you look at the whole protocol from the point of view of the participants, of the computers in the network, if you're not a miner and if you're not doing any transactions, all you do is that you listen for new transactions and you listen for new blocks. And whenever you hear a valid new transaction or a valid new block, you would just tell all of your neighbors about it. OK. And of course, whenever you hear about a new valid block, you would just add it to the end of your own copy of the blockchain. OK? So would this finally give us consensus? And actually, the answer is unfortunately still no. So it makes it much more likely for us to have consensus, but it doesn't guarantee it. Why is that? Because it might be that two different miners, maybe at two different parts of the world, get lucky at almost the same time. Maybe it happens that you find some block here in Hong Kong, and at the same time, someone else finds a valid block, solves the computational puzzle successfully on the other side of the world, let's say in the US. And then again, we will have a situation that was similar to the situation for double spending. So we have two miners, Mindy and Manny, they have each created a block that is their candidate for being block number 5, and they have both solved the problem correctly, right? But now, again, let's say one of them announces the block here, and the other one announces the block here. And then again, we have the same problem that we had in double spending. The blocks get propagated, and each node thinks that the block that they heard about the first time is going to be the valid block. So half of my nodes, maybe these nodes, would believe that block number 5 is Mindy's block, and the other half would believe that block number 5 is Manny's block. So it seems this whole idea of having a blockchain didn't really work. We still have the same problem that we had with double spending. So why do we even bother with solving proof of work and doing all these computational things? Well, the reason is that this one is now so much easier to solve, and the solution is very easy. I can just say to every node on the network that we have a new rule. And our new rule is whenever you have more than one blockchain, more than one chain of blocks, you always take the longest chain. So we tell everyone in the network to always only follow the longest chain, and the longest chain is the consensus chain. Now, why does this work? Because suppose that at some point I had a fork like this. So I had 2 different candidates for B5. Yeah, I temporarily don't have consensus now. But that's fine. At some point, someone else would solve the problem for B6. And when they do that, they have to choose which one is going to be their previous block. So if they chose, if the next miner who successfully solved the problem chose Mindy's block, then this chain has 3 blocks in it, and this chain has 2. So the longer chain wins, and then everyone in the network would just switch to the longer chain. Now, it might be that both chains grow at the same rate. Maybe they both get a new block at almost the same time again. But again, the probability of that is really low. And as you continue this process, you will eventually get to a point where there is one chain that is really longer than every other chain. And so we will eventually get to consensus. So what we have is not a perfect consensus. It's not that at every given time, everyone agrees about the blockchain, but we have eventual consensus. So eventually one of the one of the chains gets longer than all of the other chains. And then everyone on the network would just agree on that longest chain. Okay, and this actually, you can see papers on this that prove that it happens with probability 1. Okay, so now finally we have consensus. But we paid a very high price for this consensus, and the price is we have to do mining, we have to do proof of work, we have to solve that really hard computational puzzle, and we're spending a lot of money and a lot of electricity on this. And there are some studies that even say that this is affecting global warming. Okay, so yeah, this is all I wanted to tell you about the whole system and how Bitcoin works. But now I want to consider some of the most common questions that people ask about using Bitcoin, their security when they use Bitcoin, and their privacy. So let me just go through some of these questions. So here's one important question. How do I get some Bitcoin? And actually, if you think about it a little bit more deeply, where did the first Bitcoin come from? Because the way we talked about transactions, whenever Alice wanted to send money to Bob, she had to already be able to point to a previous transaction that gave the money to her. So where did the money come from in the first place? So that's one question that is remaining here. The other question is, why would the miners even bother to do this? So as a miner, if you want to add a block, you have to spend a lot of money on your equipment, your hardware, you have to spend a lot of money on electricity. It's expensive. Why would you do this? No one would volunteer to do something this expensive, right? And here's the really nice solution that was given in the Bitcoin paper originally in 2008. And the idea is that you reward the miners for their work. But how do you reward them? You reward them by creating new units of currency and giving these new units of currency to your miners. So you solve two problems at the same time. You solve the problem of where currency comes from, because you now have a way of creating new units. You have a way of printing money, basically. And you also solve the problem of incentivizing the miners to actually do the work that takes so much energy. So the solution right now in Bitcoin is that any miner who successfully adds a block can also include, let's say, a transaction in that block. And that transaction just pays some money, creates some new money, and pays that money to the miner. Okay, and this transaction doesn't need to have any other source for that money. So it's just new money that is being printed. And right now the reward is 6.25 Bitcoins for every block that you can mine. So I just checked the rate before this talk, and it's around this much in Hong Kong dollars, 945,000. Okay. So this is how new units of Bitcoin are created, and this is how the miners are paid for their services. But this reward actually keeps getting smaller and smaller as time goes on. And the reason this reward gets smaller is because we don't want to have an infinite supply of money. If we have an infinite supply of money, the thinking was that we would have a lot of inflation, maybe. So the reward was originally 25 Bitcoins per block, but it's cut in half almost every 4 years. It's cut in half every 210,000 blocks. Oh, and by the way, how did I do this conversion from 210,000 blocks to 4 years? Well, remember that I told you the miners have to solve this proof of work puzzle, and in that puzzle, they had to find a hash value that was small, but I didn't tell you what small meant. So small means smaller than some particular threshold. And that threshold changes in the Bitcoin system so that it ensures that a new block is mined almost every 10 minutes. Okay, so this is, again, a really nice design choice from the point of view of computer science. But it's awful if you think about it from the point of view of the environment, because it doesn't matter how much energy is spent on solving the puzzle. It doesn't matter how many people are taking part in the mining activity. The more energy and the more hardware and computational power you put into it, the harder the puzzle gets. And so you will still have one block almost every 10 minutes, no matter how much energy you put into it. Okay, so yeah, you can compute using these numbers that the total supply of Bitcoin is almost 21 million. So there will never be more than these many Bitcoins. This is the maximum number of Bitcoins that can be created by mining. And this limit would actually be reached in 2140. And most of it is already mined. So 19 million out of the 21 million Bitcoins are already out there. Okay. But now we have another problem here. Let's say that I'm a miner. And okay, now I'm incentivized to create new blocks, because whenever I create new blocks, I get Bitcoins that I can sell and I can use. But I have no incentive to create non-empty blocks. So as a miner, I can just create blocks that have no transactions in them. Why would I put your transaction into my block? Right? If I don't get any money for it, I wouldn't do that. And this is the part where transaction fees come in. So the solution is that whenever you create a transaction, other than all the previous things that we talked about, you can also include a transaction fee. And that transaction fee would be paid to the miner who adds this transaction successfully to the blockchain. So you're basically giving a tip to whoever solves that hard computational puzzle and also includes your transaction in it. Okay, now given that block rewards go down and they're cut in half every 4 years, this is actually now a significant amount of revenue for the miners. So the transaction fees are right now around $10 million per day. So the miners now have an incentive to actually include the transactions in their blocks. Nice. So finally, we have a working system. We have a system that gives us consensus, and we're not trusting everyone. We're not trusting anyone. We're just incentivizing everyone to act correctly. So I'm not assuming that the miners are honest. I'm just assuming that they want more money. And including the transactions into their blocks would give them the maximum possible revenue, so they would do it. And that's how the system works. Okay, but this also creates another problem. And actually, this is a problem that can't really be solved by the Bitcoin protocol, but it's a nice thing to think about. If you're a miner, which transactions would you prefer to put into your block? So usually the block size is limited. Usually you have 1,000 bytes for your block, sorry, 1 million bytes for your block. And you can't put as many transactions as you like. You can't put all the transactions that you have seen. So you have to choose some transactions. And of course, you would try to make as much money as possible. So the result of this is that there is now also some sort of a competition between the users. So if you want your transaction to get into the blockchain sooner, you have to pay more in transaction fees, because that's what incentivizes the miners to include it sooner. And okay, we will also probably see an example of an attack using this. Yeah, but now we have a functioning and quite nice system for transacting money. But let's ask even more questions. Okay, so one question that I'm asked a lot is, how fast is Bitcoin? And usually what people mean is not like the answers that you would get, like they say these many transactions per minute or whatever. What people really care about is the delay. Like, how long does it take for me to make a transaction if I want to make a transaction right now? And the answer to this is it depends. It depends on your definition. So you can make a transaction, you can create a transaction in basically no time. You can just create it on your own computer, right? But how long does it take for this transaction to get into the blockchain? That's something that you should be at the mercy of the miners for. So this is directly dependent on how much you paid in transaction fees. If you paid more, your transaction gets finalized sooner. If you paid less, it will get finalized later. And another related question is, suppose someone has paid me using Bitcoin. Let's say I'm a business owner and someone's buying something and they've paid using Bitcoin and they've given me the transaction. Can I just trust that? Can I give them what they've paid for? So let's say, I don't know, I'm selling a laptop. Someone pays me using Bitcoin. I see the transaction. I validate the transaction. Is that enough? Can I now give them the laptop? And of course, the answer is no, because I have to wait for the transaction to be finalized. I have to wait for the transaction to get on the blockchain. But even that is not enough. So it might be that I have my blockchain. Let's say this is the blockchain, and these are the blocks that are being added. And it might be that the transaction that paid me is in this block. Let's say this is the transaction that paid. But maybe later on, a fork happens, and someone else creates another block here. And then maybe that fork becomes longer. So we had this rule that the longest chain is always the consensus chain. So it might be that someone keeps adding like this. And so basically all the transactions in this part, in this block, get completely ignored because they're no longer in the consensus chain. So this is why you would hear about terms like 6-block confirmations. So the idea is that in order for you to be sure that the transaction is never going to be reversed, that the transaction is always going to stay in the consensus chain with very high probability, what you have to do is that you take the block in the blockchain that contains the transaction you care about, and then you wait. You wait until more blocks are added, right? And the more blocks get added to the end of this block, the less likely it is that this block would get out of the longest chain or the consensus chain in the future. And the rule of thumb that everyone uses and no one knows why is that people wait for 6 blocks. So they wait for their transaction to get into the blockchain, and then they wait for 6 more blocks to be added after it. And only at that point, they trust that, okay, this transaction is not going to get out of the consensus chain. But now the problem is, we go back to the first question, how fast is Bitcoin? If you don't want to risk it, and if you want to wait for these 6 confirmations, as I said before, every block takes almost 10 minutes to get created. So if you want to wait for 6 blocks, you have to wait for an hour. And this is an hour after your transaction was already added to the blockchain. So in practice, it's more like 70 minutes, 80 minutes, something like that. So if you want to buy something using Bitcoin, you can't buy things that have instant delivery. You can't use Bitcoin normally in a vending machine. Of course you can, and there are vending machines that use this payment by Bitcoin, but they don't wait for the confirmations. They don't wait for more blocks to be added after their transaction. So that's risky. They might get ripped off. Okay. Let's continue with more questions. So I talked about your identity on the system, and I told you that you basically have 2 keys. There is the public key that everyone else knows, and there is the secret key that only you know. And in order to create transactions, in order to send your money to someone else, you needed to sign those transactions. And in order to sign, you needed to have your secret key. So what happens if I lose my secret key? So a lot of people treat this like losing the password to their bank account, but this is not similar at all. If you lose your secret key, you have lost all of your money. There is no way you can access it ever again. Because the only way you can create a transaction is if you have the secret key and you can sign with it. And there is no central authority, so you cannot go to someone and say, I forgot my password, reset the password for me. That doesn't exist. So don't lose your secret key. This is a decentralized system. No one can control what you do. There is no central bank. There is no government. But of course, this gives you a lot of privacy. But the downside now is that you're in charge of your own secrecy and you're in charge of your own funds. So if you lose your secret key, you've lost all of your money. Another similar question is, what if I transfer money to the wrong account? So let's say I wanted to send money to someone, but I sent it to someone else. Well, again, there is no central authority who would help you recover that money. So the only way that you would get your money back is if that person sends it back to you. And that's completely under their control. And actually, there is even a worst case here. And that's the case where you transfer money. For example, you have a typo when you're creating the transfer. Maybe you put 1 space extra or something like that. And you transfer to an account that does not exist. You transfer money to a public key for which no one has a corresponding secret key. Then that money is burned forever, and no one can access that money ever again. So in terms of security, you have to be very careful what you do when you're using Bitcoin. And actually, for end users, you would usually just install an app or a browser extension, and it keeps track of all of these things for you. It doesn't even show you your secret key. It's just saved somewhere there. But in any case, if you lose it, it's lost forever. Okay. Even more questions. So another common question is, am I anonymous on Bitcoin? And I kind of answered this before. I said the answer is yes and no, in the sense that you're not transacting with your real world identity, you're just transacting with a pair of keys. And ideally, if no one can connect your identity on the blockchain to your real world identity, then you would have perfect privacy and you would really be anonymous. But what happens in practice? So let's say I create a bunch of keys, I create an account today, and I keep transacting using this account. Maybe I even do some things that are illegal. And then, I don't know, I buy drugs, let's say, using my account. And then sometime in the future, for example, 2 years from now, I use the same account to buy a coffee at Starbucks. Now, what happens here? Well, Starbucks probably has a camera in their store, so they can connect my blockchain identity to my real world identity. So they would know what was my identity on Bitcoin. And normally that's not a big deal. Like if you use a credit card, you have your name on the credit card and the main merchant can probably see your name and they can connect your credit card number maybe to your real world identity. But in Bitcoin, this is a huge problem because remember, all the transactions are on the blockchain. Everything that has happened in the past is on the blockchain and everyone has a copy of the blockchain. So as soon as your blockchain identity is connected to your real world identity, they can see all the transactions that you have ever done using that identity on the blockchain. So it's similar to a situation that, okay, let's hypothetically consider this situation. Let's say I go to Starbucks and I buy a coffee, but not only they can see my credit card details, they can also see all the transactions that I've done with this credit card in the past. So yeah, be very careful about that. Be careful about not connecting your anonymous identity on Bitcoin to your real world identity. Okay, but the question is how? So if I'm a Bitcoin user and I want to preserve my privacy, if I want to make sure that no one can connect my identities, well, one way is you can just create as many accounts as you like for Bitcoin. So just create many accounts and don't use the same account for everything, which is the mistake that actually, I think there was a paper recently that said more than 80% of Bitcoin users use a single account during their lifetime. And you shouldn't do that. You should actually create a new account for every new transaction that you want to make. But even that doesn't give you perfect privacy. So what does? There are actually services called mixers. And you would need these services to get more privacy. Now, how does a mixer work? Well, a mixer has actually a very simple idea. So let's say I'm a mixer. I take money from 10,000 different people. Each one of them just pays me 1 Bitcoin. And then I pay this 1 Bitcoin back to them at a new address. So if you want to use the services of a mixer, you have money in your old address, you create a new address. You send your money to the mixer. A lot of other people are also sending their money to the mixer. This is basically laundering money. And then the mixer sends back your money to your new address. So no one can connect the old address to the new address, and now you can transact with your new address. And even if someone can connect your new address to your real world identity, they will just see your transactions until the point where you use the mixer. But now another problem is, can I trust the mixer? Because what if I just send my money to the mixer and the mixer doesn't pay me back in the new account that I was hoping he would pay me back? Well, again, there are no central governments or central authorities here, so you can't do anything. If you send your money to a mixer and they don't pay you back, you've lost your money. Yeah. Now, the good point here is that there are some protocols that implement a trustless mixer. So there is a way to have a mixer that is not really under anyone's control, and it's also decentralized and all of these things. And so those mixers are trustable. They can't steal your money. But I will need like a lot of time to explain how that would work. Maybe just take my course on blockchains and you will see how this works. But anyway, these days, you have to either use a mixer, and you have to use a mixer that you trust, or you don't really have privacy on Bitcoin. And actually, the problem with mixers is not just that they might steal your money. It's also that I can't trust them with my privacy, right? So I have two accounts. I'm sending my money to the mixer from the first account and asking the mixer to send the money to my second account. Now, everyone else on the blockchain is unable to connect my first account and my second account, my first blockchain identity and my second blockchain identity. But the mixer knows both of these. So the mixer himself or herself can actually connect the two accounts together. So the solution for that is, don't use a single mixer, use 5 different mixers back to back. And then hopefully you can trust at least one of them. Okay, so we're getting towards the end. So another question is, how decentralized is Bitcoin? Now, I gave you a definition of decentralization at the beginning of this lecture. And in that sense, Bitcoin is perfectly decentral, right? There is no central authority. Everyone has the same access permissions and can do exactly the same things. But usually when people talk about decentralization, they're actually talking about control, right? So how many people or how many organizations actually control Bitcoin? That's the question that we want to answer. And in that sense, Bitcoin is not really decentralized. And in order to see that, you have to understand what a 51% attack is. Now, a 51% attack can happen when someone or a group of people have more than half of all the computational power on the network. So let's say I'm an attacker, and let's say I have more than half of all the computational power. This would kind of seem impossible with today's numbers and with so much computational power that exists on the network already. But just assume for a second that I have more than 50% of the computational power. So what can I do? Let's say this is the blockchain right now. And let's say that I see a transaction here in the blockchain that I don't like. I have more than half of the computational power. So I can just create a new block here and basically fork from here. But this wouldn't work just like this, because we said that the longest chain is the consensus chain. So I just keep working here and I just keep adding more blocks. And I do this until my fraudulent new fork becomes longer than the other consensus chain. And now I've basically forked the blockchain, I've rewritten the history, and I've changed all the transactions that were there. I have removed all the transactions that were here, and I've added all the transactions that I liked here. Now, the only way I can do this is if I have more than half of the computational power, because otherwise the honest chain would actually grow faster than I'm growing my fraudulent chain. But if I do have more than half of the computational power, I can do this attack. So now this is the part where things get scary. So any group of people or organizations who have more than 50% can basically rewrite the history can remove any transaction that they don't like, can add any new transactions that they like. And right now, this is how the computational power is distributed on the Bitcoin network. So there are basically 3 large mining pools. These are like organizations that mine blocks. And these 3 large mining pools together have more than 50% of the computational power. So I don't know how exactly each of these mines are managed, but if you can just make these 3 guys who are at the top of these 3 mining pools to collaborate with you, they can rewrite anything on the blockchain. So it's not as decentralized as you would hope. Of course, there is some weaker guarantee, and the weaker guarantee is that these people, they basically have companies and their livelihood depends on continuing Bitcoin. And if they do an attack like this, then Bitcoin would lose all of its value and no one would buy and sell Bitcoin anymore. And so they lose all of their investment. There is that argument. I don't know if you buy it or not. I'm a computer scientist. I don't want to talk too much about economics. But just know this. Know that there are 3 people in the world who can change the history of Bitcoin and basically remove all transactions and add new transactions. Okay. So some more questions. Why are there so many other cryptocurrencies? Why don't we just have Bitcoin? Well, the first answer is most of them are jokes, and most of them are just some fake thing that someone created, and they're usually just copies of Bitcoin, like Dogecoin. And it doesn't make any sense that they exist, but they do. But some of them actually exist because they have better alternatives and better choices for some of the things that Bitcoin has done wrong. So for example, we have cryptocurrencies that don't use as much energy. We have cryptocurrencies that don't use proof of work. They use something else called proof of stake mostly. And so they're more efficient. Some of the other cryptocurrencies that exist actually make it so that we can reach consensus faster. So they're useful in that sense. And yes, and most of them are just not useful, honestly. Now, another question is, what is a smart contract? You might have heard about this a lot, or if you haven't heard about smart contracts, you have definitely heard about NFTs, which are like a special type of smart contract. So some blockchains like Ethereum actually allow you to put code on the blockchain. So you can take a program, a computer program, and you can put it on the blockchain. And then this program, which is called a smart contract, can receive money and can manage money according to its code. So I can, for example, create a code, a program that says, get as much money as anyone else pays you, and then pay this money only to someone who can solve a particular problem, or pay all of this money to me. Right? I can create this code and I can put it on the blockchain, and then anyone can send money to this piece of code. And then this piece of code works exactly as it's coded. So that's what a smart contract is. And almost all of the NFTs are smart contracts. Okay. Finally, last question, should I invest in crypto? Personally, for me, the answer is no, you shouldn't. But it's none of my business if you want to lose your money. So do it. But just know the risks. Know that there are 3 guys who can change everything. But if you think that's worth it, if you think you can invest in it and get some easy money, do it. None of my business. Finally, if you're interested in this topic, this is a really nice website that teaches you how to write smart contracts. And you can also take my course, which is going to be offered next semester, and it was also offered last semester. So that's Comp 4900W. And that's it for me. Have a nice time. Bye.